This is another example from section 3.8 on related rates. And this problem is a little bit more of a challenge than the previous couple examples. I think it's an interesting problem myself, and it was one that my Calculus 1 teacher did with our class. So shout out problem credit to Mr. Steve Hauk, who inspired me to get into teaching math. This also is one that I like because it relates to my hometown. So here we're looking at a mountain, Sawtooth Peak. It's about 3 miles tall and lies 40 miles from the town of Visalia, which is where I grew up. As the sun rises, the edge of the mountain's shadow moves across neighboring fields and towns. How fast is the edge of the shadow moving when it falls on Visalia? Okay, now this is something that does actually happen as the sun rises in the morning. It comes up behind the Sierras over there. And yeah, as the sun appears to move across the sky, the shadow of the mountains gets shorter and shorter until the sun is overhead. So yeah, it's kind of an interesting problem here. So for starters, let's sketch it out. That's how we start these related rates problems. And let's draw Sawtooth Peak over here. A very technical drawing of the mountain. Okay, and here's all the little towns down below. There's some foothills in between there. Okay, and let's put the little town of Visalia right here. Visalia. Okay, you can put some little buildings in there if you like. Cute. All right. Now we would like to label what we can with variables or constants. So since the town is not moving, let me actually erase that V there. Also, the mountain we can assume is not changing height. Okay, I mean, to some degree, perhaps maybe it is a little bit due to erosion and things, but on the scale that we're looking at, we can assume that 3 miles tall is pretty darn constant. Okay. And this 40 miles here, that does not change, but the distance that we're going to be labeling here is not so much that 40 miles, but it's actually going to be the length of the shadow, or this location of the edge of the shadow. Because, okay, here's the sun up here. Okay, sunshine. And as the sun shines down, okay, it's going to hit the top of the mountain and cast a shadow. And when the sun is lower in the sky, okay, you can see that that shadow would be, well, in this case where I drew the sun, a lot longer, too much longer, casting a shadow somewhere over there. So the little town of Visalia would be completely in shadow at that point. It's pretty early on in the morning. But yeah, that shadow length is going to change as the sun moves across the sky. So there's our shadow length right now. And then the sun would get higher and cast a shorter shadow, etc. So that's really what we're looking at here, is that shadow that's being cast. And this is the shadow length. I'll call that S. Okay, and that's one of the things that makes this problem a little more complicated to think about. So, shadow length. All right, now let's identify what we want to find here, and then we'll continue thinking about things. So we want some quantity here, and you look at the problem and it says, how fast is the edge of the shadow moving? So that's what we want. You could actually start out by writing that. Speed of the edge of the shadow, perhaps. Okay. Which you have to think about in terms of what we've labeled so far. The speed of the edge of the shadow, well, the edge of the shadow would be moving like this. And so what's being affected that we've already labeled is the shadow length, S. As the shadow's edge moves in closer to the mountain, the shadow length is going to decrease. All right. So this would be a rate of change of shadow length S. All right. So we know that we are looking at these rates of change at particular moments in time. And so that would be the derivative ds dt. Okay, so we want ds dt. And we also want that at just a particular point in time. Okay, we want ds dt when? Okay, when the edge of the shadow falls on Visalia. So that shadow length, let me label this a little bit differently. This might help folks. All right, so the shadow length, let's say, goes out a little longer here. All right. And from the town to the mountain is 40 miles. Okay, how about we label it like that a little better. Because that shows us more what we're looking for with this instant. We want this, the instant the edge of the shadow falls on Visalia. So when that shadow length equals 40 miles, that's the moment in time that we're looking at. So this is when S equals 40 miles. Okay, lots to think about here. Okay, so let's see what relationships we can come up with. All right, relationships. And this is one of those problems where, yeah, you might have to try a couple different things just due to the nature of the problem. You might observe here that we do have a right triangle, and that is going to be helpful for us. Right triangles have some good properties, good relationships that we can utilize here. So you might think about something like maybe a Pythagorean relationship, like s squared plus 3 squared equals, I'll just call that h squared for hypotenuse. But then we think like, okay, well, we don't actually have very much information about this hypotenuse here, h. You might be able to come up with some working for that, but we don't really have too much information about how that's changing. And this really is the only relationship that we have for the length of that hypotenuse. So I'll put a question there. But to maybe avoid introducing another variable here, we could work with what we have right now more. And notice that we have S and 3, just those two sides of the triangle. There is a relationship that we could use for that one side over another type of ratio there. We could use our trig functions on this because this is a right triangle. So let's call this angle down here theta, because that angle theta is actually giving us the kind of angle or position of the sun relative to the shadow length. So that's kind of a useful thing to have. So maybe let's try the tangent relationship. Tangent of theta would equal opposite over adjacent, so that would be 3 over s. 3 over s. And this actually is going to turn out to be the workable relationship here. Now, if you do come up with a way to use this Pythagorean relationship and come up with the same result, please send me an email, let me know, because if there is another way to do this one, I would like to know it. I just haven't come up with another way myself other than this tangent relationship here. But yeah, if you want to play around with it, that'd be cool. All right. So this tangent relationship turns out to be workable because we are going to be able to find information about that angle theta, about the positioning of the sun here as it moves or appears to move across the sky. So this one turns out to be workable. If you try this Pythagorean and are not able to make it work, you'll notice because you won't be able to find values for things that you need, which can be frustrating, but it does happen. So, okay. So this is going to be our winner here. Okay. So now we need to differentiate that with respect to time so that we can get some rates. I'm going to rewrite this 3 over s as 3s to the negative first power instead. All right. And so we're going to differentiate with respect to time t, d dt of tangent theta. And remember that theta is a function of time, t, because that angle theta will change as time changes, time moves forward. And then we'll have d dt of 3s to the negative 1. And remember that s also is a function of time t, because the shadow length will change with time. Okay, so these are implicit derivatives, totally. And so we'll take the derivative of tangent, that's secant squared theta, times d dt of theta. And then the derivative of 3s to the negative first would be negative 3s to the negative 2 times d dt of s. Okay. And so to clean up those derivatives a little bit, we'd have secant squared theta d theta dt equals negative 3 over s squared times ds dt. Okay, now notice that we do have our rate that we are actually trying to solve for here. Okay, ds dt, this guy. Solve for that. And so let's multiply by negative s squared over 3, and that'll give us a nice equation that is solved for ds dt. Okay, so negative s squared over 3 secant squared theta d theta dt. Okay, now we should look at what we have values for and what we still need to find here. So notice that we do want this rate of change ds dt when s equals 40 miles. So we do have a value for that. Okay. Whoops, I don't want that pen. Let's see, how about this? So this is when s equals 40 miles, so that's checked off. We got that. 3 is a constant. Secant squared theta. We do need an angle for theta. So theta we'll need to find that, but notice how we can find that actually based on the fact that we know what we want length S to be. S here equals 40 miles. This side for the mountain is still 3 miles. And so we could find theta based on that. Okay, so theta, you could say, is the inverse tangent of 3 over 40. All right. And we'll just leave it as that for now. And let's see, we've got S, that's going to get us theta. And then for d theta dt, that is the rate of change of our angle theta as the sun moves across the sky there. Okay, so this is for the rate of the sun's movement across the sky. And I put movement in quotes there because remember that it only really appears to us like the sun is moving. We are actually moving around the sun. So yeah, and Earth is spinning on its axis. That's what causes the sun to appear to move across the sky. Yeah. So the sun is not actually moving. Let me make that clear. Don't like call the physics department on me or something. Yeah, we're moving. The sun is staying still, but it looks like the sun is moving. Okay. So what is causing that movement again is the fact that we are rotating on our axis. And so the sun looks like it's moving. So Earth rotates on its axis 1 revolution per day. Okay, so that is actually going to give us our information for this rate of change here. 1 revolution per day means we're going to travel 2 pi radians per 24 hours, you know, roughly speaking. And so to get d theta dt, that would be 2 pi radians in 24 hours. Or we could simplify that to pi over 12 radians per hour. And notice how I'm not writing radians, because usually radians turn out to be unitless in a lot of unit calculations like this. So pi over 12 hours. Okay. So that is our rate d theta dt. And so now we have actually gotten values for everything that needs to go into this equation. And so we're going to take a little more space than I initially planned. This is for the next example. Example number 4, I'm going to leave for you guys to try on your own, actually, because it is actually easier than number 3, and I think you guys can do it. It's a circular pattern. So try that one out after you watch this video. I think it will feel refreshingly not as crazy as this problem. Okay. So yeah, now that we've gotten values here, we're going to plug them in. ds dt equals negative s, which is 40 miles, getting squared over the 3 miles for the height of the mountain. There we go. Okay. And then we have secant squared of theta, which is the inverse tangent of 3 over 40. And this trig function is unitless. Okay. And then d theta dt, we just found to be pi over 12 hours. Okay, so we've plugged everything in. And to investigate our units first, we have miles squared over miles. So that would leave us with just miles in the numerator. Okay, so units will have miles in the numerator. All of this portion is unitless, 3 miles over 40 miles inside of tangent inverse there, and then doing secant squared, that doesn't add any units to this. And then pi, the radians again, are assumed to be unitless. And then we have over hours. So units are miles per hour. Shoo. Okay, that's good. We actually want that for ds/dt because s is measured in miles, time t is being measured in hours. So that is wonderful. Okay, now this, definitely feel free to plug into your calculator. There are some other ways to calculate this, which I might go over after we kind of finish this way of looking at it. But if you plug this all in to your calculator, be careful, especially with your trig here. Use the arctan or tan inverse button. Yeah, if you plug this in very carefully, you should end up getting a nice even negative 140 miles per hour. Okay. And while that value might seem a little large, first off, notice how this is taking into account the movement of the edge of a shadow that is being cast by the sun. And it's a really long shadow at that. So the fact that this is moving rather quickly is actually semi-reasonable. If you've ever seen, like if you've been out on the road in the morning near the mountains, you can see the shadow move as you're driving. Or if you're driving and you're in shadow at first, it won't be long until the sun is hitting you in the face. So yeah, it is actually a reasonable value. And then also the negative is reasonable because that indicates a decrease in length. And the shadow length is actually decreasing as the sun rises, okay? So the decrease makes sense. The value, while large, is reasonable, and the units came out reasonable as well. So there is our ds/dt there, negative 140 miles per hour. Okay. Now, to go over a few other little things, if you were just here for the solution and that's it, that's cool. You can turn the video off now. But if you want an alternate way to think about this, let's try some stuff. Let me actually just get rid of number 4 for right now. Again, you can do that one after this video. Okay, so some other ideas about this. This will make a really long video, but hey, you know, you can watch it on double time or you can stop watching it at this stage. We solved the problem. So for one thing, you can actually calculate this tangent inverse, secant squared of tangent inverse 3 over 40. You can calculate that in a different way. So I'll just label this as like alternate stuff. Okay. For our angle theta, we had this setup with the right triangle, 3, 40, angle theta right there. You could use Pythagorean Theorem to find this third side of the triangle, to find the hypotenuse length there. So you could do that equals 3 squared plus 40 squared equals hypotenuse squared. And that turns out to be 1609 equals h squared. So the hypotenuse here is the square root of 1609. And you can even just leave it as that radical for right now, because all we end up doing with that angle theta, as far as plugging things in here, is finding secant squared of theta. So you could find secant theta from this triangle being 1 over cosine theta. And so cosine would be adjacent over hypotenuse. So secant would be hypotenuse over adjacent. So that would be root 1609 over 40. Okay. And then for secant squared theta, you would take that value and just square it, which would end up canceling out the radical in the numerator. And that's what comes out kind of nice about this. You'd get a nice 1609 on top and then 1600 on the bottom. So 1609 over 1600 for that. So when we do our ds dt calculation, you can put that in. So we would have our negative s squared over 3 miles. And then this would be our secant squared value, 1609 over 1600. And then we would have our pi over 12 hours for this portion here. Okay, and turns out actually since the 1600, that is from 40 squared, that's going to just cancel out that numerator right there. So you'd have ultimately negative 1609 pi over 36, okay, miles per hour. And I think I might have said that this turns out nice and even above here. That is actually an approximation, negative 140 miles per hour. Because yeah, we've got pi in there. There's no way that that turned out perfectly evenly. So there's another way to get that approximately negative 140 miles per hour. Okay. Now you could actually also find the value of angle theta. Remember to do that in radians, since we are working with radians here for the angle of the sun changing. So you could do that, but then you'd probably want to just keep that value in your calculator anyway. That way you could use it to find secant squared. So that's one kind of alternate thing. And then the other alternate thing that I would want to explore here maybe a little bit is, what if we had tried to use this other relationship, the Pythagorean one? Now, let's see, let me get rid of problem number 5, clearing space here. I'll do that one in a video for you later. So let's try other relationship. Because yeah, sometimes, you know, it's good to see how things would work out, to just see what the process of playing around with this stuff looks like. So if you had gone with that s squared plus 3 squared equals h squared and not really worked with the angle theta, let's see what's up with that. You would take the derivative of that with respect to time t. Okay. And for this first term, d dt of s squared, that's going to be 2s ds dt. So we do actually have the rate that we're looking for there. Okay, that's good. And then you'd have plus 0 from that second term. And over here you'd have 2h dh dt. Okay. So that might not look too bad initially. Let's see. We could divide both sides by 2. Okay, divide by 2, divide by 2. That would cancel our 2's out. Okay, we'd have s ds dt equals h dh dt. And so we'd have ds dt equals h over s times dh dt. Okay, now let's see here. We could find a value for h, not bad. Okay, for h, we would just use that triangle that we had up above here. Okay, this one actually. So h is the square root of 1609. So h, c above, h equals the square root of 1609, and that is in miles. But then we come to the interestingness of dh dt. And that's the one where I am not quite sure how we would finish this problem out. I mean, we've got S is 40 miles, but for dh dt, you would have to find out how that hypotenuse length is changing over time, which you probably could work that out if you looked at the angle theta again, but then that would require you to look at theta, and if you're going to work with theta anyway, then you might as well use this other relationship, in my opinion. So yeah, if we could come up with some other way to figure out dh dt, this Pythagorean relationship would be probably easier to work with, but that finding dh dt is hard to come up with. So yeah, not 100% sure how we would do that, since ds dt is the thing we're trying to find. 3 is not changing. I really think you would end up having to use that angle theta, which again would be doable, but then you'd still have to work with like this rate of change of theta, sun moving across the sky type of thing. So yeah, if you want to play around with that again, let me know if it works out nicely. But at this stage, I think we would have to just use theta anyway. So would probably need to use theta anyway, in which case we could probably just go back to the previous method of solution. But that also kind of brings up the point that, yeah, if this was the only relationship that you saw, you probably could make it work. It would just take more thinking at a different stage in the problem. You'd have to do more to find dh dt, but I think you could actually make this work one way or another. So yeah, something worth considering. But again, this is a challenging problem. This is, I'd say, more challenging than anything I'm going to put on your test. But it is just kind of nice to see a hard problem here, to know what these related rates problems can be like. They are not always pretty. They don't always turn out, as nice as you would expect. And the numbers in this one have even been simplified to some degree to make them a little better to work with. So yeah, things in the real world can get quite messy. So just remember that if you ever come across one of these in the wild. Okay, I think we'll wrap it up there for this example. Go ahead and try example 4. Again, it is not as complicated as this problem. It's a circular pattern. Focus on that idea. And I think you can do it. And then check the completed notes to check your solution. So go ahead and try that.